have the
Alex!
Okay, so, first slide. So what is Fenton's reagent? Discovered in the 1890s by a British chemist named Henry John Fenton. He dissolved, the main two chemicals he dissolved were trichloroethylene and tetrachloroethylene. The first one being dangerous chemicals found in waters, and the second being chemicals found in like dry cleaning supplies. So it's the mixture or the reaction of iron 2 and hydrogen peroxide to create iron 3, which gives off an electron to the hydrogen peroxide, separating it, and then a whole lot of reactions which result in water and hydrogen dioxide, which is has an O radical, which is very reactive, and that's what's breaking up organic compounds. So ideally, what will happen in Fenton's reagent is it completely dissolves, or it completely destroys the compound, making just water and CO2. So as some of you might know, plastic is an organic compound, meaning I was trying to dissolve the plastic and then run Fenton's reagent in order to eradicate it instead of waiting the 450 years. Okay, so at the beginning of the year, I did a test to just show that Fenton's reagent works. So these are just water, and 2 of them had food coloring, and I ran Fenton's reagent on the 3rd one, the 5th one, and the 7th one over there. This is toluene. It's tonic water, which has toluene in it, which glows under UV light, and that one is fluorescein, which glows under UV light. So after running it, this completely got rid of the green food coloring because it's an organic compound. In green food coloring, toluene is an organic compound, so it completely made it completely it doesn't glow anymore. And the fluorescein is now a more yellow color instead of bright green. So to test to make sure that the compounds actually were eradicated, I ran through a GC, which I'll explain now. A GC is this machine. It's small. Usually they're a bit bigger, like around this high. Those will be $20,000 though. This is a $2,000 one. And a GC basically separates the compounds, but I'm not separating them entirely. I'm only injecting 1/10 of a microliter to a 1/5 of a microliter. So basically when it's on, you take the organic compound, put it in here, and then when you inject it, it collects it on a graph, making graphs. I'll show the graphs now. So it makes graphs like that, which you read based on time and the concentration that the chemical comes in. So every organic compound has a specific peak due to its weight and if it sticks to the column being a several, I guess, meter long tube that has inert gases or inert solids or liquids so that the compounds won't react with them, and it only add here so it bounces off. So based on the type of the compound and the weight, it will take different amounts of time to come through, and that's how you identify the compounds. Yeah, so when I did this with acetone, I first diluted the acetone, injected the acetone into here, and then to see if Fenton's reagent would work, I took zeolite, which is a natural filter, so that way it'll filter the water better. And I did this substitute with iron sulfide to make it iron sulfide, or to make the zeolite instead of sodium zeolite to iron zeolite, so that the Fenton's reagent would happen. So instead of this white powder, it's now this brown powder that I would mix with hydrogen peroxide. So that's the before the Fenton's reagent, and after it was almost zero, meaning that the acetone was no longer a compound, it was all CO2 and water. Almost completely clear, a very small peak. So yeah, now the plastic, that's what I was working on the 2nd semester of the project. So that is polyethylene found in all plastic materials. I worked with mainly water bottles because that's what seemed to dissolve in plastic and they're the most accessible. Plastic bags didn't work with the phenol. So I used phenol. When dissolving it, I originally thought that it was just dissolving it so that it wasn't making a new compound. It turned out it was reacting. So it makes resin, and then you need the water in the thing so that the iron zeolite would dissolve into it and Fenton's reagent would work. But when I put water into the phenol, it was like separating into the plastic and water. So that was I only had about like 5 minutes to inject it and run the procedure, or else it would separate and I would have to restart the entire process. So that was the first graph of the phenol with plastic before I ran Fenton's reagent. And as you can see, phenol, I didn't put a graph here, but phenol is at about like 16 minutes that it'll peak. So that shows that it's not phenol anymore, it's a different type of compound. And then after Fenton's reagent, this is also 5 minutes, so it's about the same time. This is only 30 minutes of Fenton's reagent. The second one, which I'm about to show you, ran for 4 hours. But so it's about the same peak, but I do believe it is a different compound because although this is not a good peak because it's widespread, you want it to be very thin and happen in about like 10 seconds or less. They're about the same, but the next one is at 4 minutes instead, so meaning that it's a different compound now. I don't know what, because we don't have a mass spectrometer in the lab, so I wasn't able to analyze the compound. But then the second time I ran it, it was actually 2 different compounds. I ran it for longer, and I unfortunately don't know what those are either, so I'm not totally sure what it made. It's non-volatile, as I checked just right before this. The liquid didn't evaporate into the fume hood, so it is probably an acid, and it is probably less dangerous than the plastic, meaning that you can handle it and get rid of it without having to wait for it to biodegrade for 450 years. And that's my research. Questions? Yeah.
So what implications do your findings have?
That there is a way to dissolve plastic and get rid of it instead of having to wait the 450 years. Phenol costs about $100 for 500 milliliters. So the price after doing a bit of math would be about 38 billion a year to get rid of 8 million tons of plastic. So that's just offsetting the amount of plastic that's pumped into the earth every year. So to do so for the last like 30 or 40 years, it would probably be around $150 billion to get rid of the plastic. And then also the time that it takes for workers to do it. So although it's not cheap, it's definitely better for the environment. Although CO2 is also dangerous for the environment, so that's the next thing that would have to be worked on is carbon capturing.
Well, sorry, okay. When you work with the plastic, you use the zeolite.
Yeah.
Could you have done it without the zeolite?
So you probably could have. I didn't test it. We didn't. I don't know if I didn't actually look at this. I didn't know if we had an iron 2 in the lab, which you do need. If we did, I could have tried it. I don't know if it would have worked any differently. I'm gonna try and do this project, continue it in college, where I have more resources.
Is there an advantage to using the zeolite, do you think?
Because it's a cage and it's a natural filter, I do think there is a advantage.
And that that peak right there, what could you do in the future to define the 2 peaks?
So the mass spectrometer that I found earlier is just, I'm not exactly sure what it does because I haven't worked with one, but it takes the mass, and each compound has its own mass for the most part. So I'd be able to, based on that time that it came through the graph, I can look at its mass and then check it with other masses or other compounds that have a similar mass and a similar time.
True,
but
like you have to define those peaks first. How could we try to define those peaks better?
Yeah. So better GCs, better than that one that I would have in college, can go to a higher temperature. Phenol's boiling point is 180, and that only goes to 160, so it's not necessarily a gas when it's going through, which is another big problem why they aren't very defined. Yeah.
So you get the plastic in solution, right?
Yeah.
And is the reverse to the reaction reversible? Like, can I remake plastic after that? Or not?
So I let it sit for I think like an hour, or maybe, I don't know if it was an hour or like a bit more, and it completely solidified. So I don't think it is reversible.
I see.
Yeah. Mr.
Going back to the GC for a second, I know you said the temperature is an issue. Could you just swap columns? Like, is there a better column we could use with this GC?
Well, they're all inert gases. The other problem is this doesn't use an inert gas to pump it through. It uses air.
Right.
The other problem is it just doesn't go to a high enough temperature.
But there are columns with different compositions you can buy, right? Have you looked at
That's
that?
true. I don't think we tried to research it. This one isn't very isn't a very good GC. It doesn't. You can't replace the column at will.
Okay.
Yeah.
Is there any concern about handling or disposing of the phenol that you're using?
Probably.
You
I
might
mean,
want-
in theory,
Thank you.
it goes to just water, and it's CO2 and water, so there wouldn't be need for disposal of it. In theory,
But
yes.
you might, just in handling, you might wanna look into it.
Yeah.
Yeah.
Last question, since he's out of time, so I'll ask him.
So you said that in theory it was like just water and CO2, but in your experiment, what did it end up going to? Water, CO2, and was there
So
anything else that you
water, CO2, that's where the peaks are. So the peaks are the compounds. Like if I had more equipment, I just don't know what they are at the moment.
But there are things in your experiment that also popped up instead of just water.
Yeah, so those are not water is 0 on the GC, so it would be some other compound.
Yeah, we're assuming those are carboxylic acids.
Yeah.
Are those hard to get rid of?
No, if you ran it longer, you might actually get rid of the carboxylic acids also.
Oh,
Good job.
thank you.